Good afternoon, everyone. Welcome to day 4 of our FDP. We are happy to have you with us as we continue our long journey together. Now, I invite Ms. Jisha Kara, Assistant Professor, Jyothi Engineering College, to introduce the speaker to the audience.
Good afternoon, everyone. A warm and heartfelt welcome to the insightful session of our FDP on innovations in civil engineering, integrating geospatial technologies, structural monitoring, AI, and sustainability, organized by Jyothi Engineering College. It is my privilege and honor to introduce today's subject expert, the esteemed Dr. Niti M., Assistant Professor in the Department of Civil Engineering at the National Institute of Technology, Puducherry. Dr. Niti is a well-recognized academic and researcher whose core areas of expertise include structural concrete, beam column joints, fiber reinforced concrete, sustainable concrete, and forensic engineering. She is actively involved in leading research groups such as the SEM, Sustainable Concrete and Innovative Materials, and the Structural Engineering Research Group. She has published extensively in high-impact journals and has presented her work at numerous national and international conferences. Her recent research delves into the application of machine learning models in sustainable concrete, an exciting area at the intersection of structural engineering and artificial intelligence. Among her many accolades are the ICA Ultratech Endowment Award for her outstanding PhD thesis and several Best Paper Awards, most recently at the Dept 2024 International Conference. With her deep experience in both research and consultancy, including collaborations with institutions like IIM Trichy and CPWD, she brings an exceptional blend of theory and practical knowledge to today's session. We are truly honored to have her with us as subject expert for this session, one that aligns perfectly with her research vision on structural monitoring, AI, and sustainable civil engineering. Dr. Niti, we extend a very warm welcome to you, and we look forward to an enriching and engaging session. Over to you, ma'am.
Thank you so much. Good afternoon, everyone. Special thanks to Jisha Madam for this wonderful introduction. And also I thank the organizers of Jyothi Engineering College for inviting me again for this FDP. So it's always a pleasure to give a lecture to Jyothi. Thank you. Hope I'm audible.
Yes, ma'am.
Okay. So shall we move on to the session?
Yes, ma'am.
Yeah. Is my screen visible?
Yes.
Okay. So basically, this session is about structural health monitoring of slender masonry heritage structures like minarets. So this project is collaborated with CDRI and Archaeological Survey of India. So it's as per a funded project from CDRI. And I would like to start the presentation and see the concepts mainly when we went to the field and taken the data and have done the structural health monitoring analysis and also the structural dynamics part, and then its application, how this same thing can be done using AI techniques. So that's what I have intended to include in this presentation. So here goes outline of the presentation. So first we'll discuss about the structural health monitoring. and then various steps involved in the structural health monitoring, and what all should be monitored, how to monitor, and why should we monitor all these. And regarding the slender masonry structure, so in this study, I have mainly focused on this slender masonry structures, that is the structural minarets. So then the case studies, and then finally the conclusions. So over to what is structural health monitoring. So can any one of the participants tell me what is structural health monitoring? I prefer to have a discussion because I don't prefer a monologue conversation. So then only I can ensure that somebody is there on the other end. I hope I'm audible. Hello. Okay, so okay, I think the participants can't speak. Is that so?
Yes, ma'am, actually, to avoid any kind of
Okay,
issues.
all right. Okay, so anyone can put in the chat also. I want some response.
Okay, we have unmuted the participants for the time being, so you can
Okay.
speak.
Yeah, so what is the idea about structural health monitoring? Any response? Yeah, so it is a continuous assessment of like how to integrate the like how to monitor the structure. So for example, in this slide, I have just put one. Yeah, so similar to we going to a doctor after getting a disease or some symptoms we are having. So we go to the doctor, and what does the doctor do? He will just put the stethoscope or even advise us to do some medical test, for example, blood test and all. So from that result, he will suggest what repair method or what medication is needed for your condition. So similarly, a structural health monitoring engineer also monitor the structures and then suggest the remedial measures and assess the present condition, and suggest the remedial measures. So it's a process of implementing a damage detection and characterization for engineering structures. Now, the damages can be due to various reasons. For example, mismanagement in the construction. So during the construction itself, there are some mismanagement happening place. So I'll just put my, some mismanagement during the construction. And obviously lack of quality control. We always see everywhere there is a problem in the quality check. And also due to variation of temperature. Then maybe due to some cyclic loading, the damages in structure can occur. And it can also occur due to the geometric property and boundary condition. Boundary condition generally represents the support condition. If there is any misalignment in the structure or any changes in the boundary condition and all, it can occur. And also the different characteristics of the system. So why we should use structural health monitoring? So it is to ensure the safety, and also we can like replace the schedule driven maintenance based on condition based maintenance. What it means is that normally what we do is a routine maintenance, like every year this period of time we will go for the maintenance. So without looking at the condition, even just routine maintenance we follow. But in condition assessment means we check the present condition of the system or present condition of the structure, then only we'll go for the monitoring. So maybe it can be like twice a month we can go or something like that. So based upon the condition, present condition, we can do the assessment. For example, now we inbuilt the sensors in the bridges and all, so we can monitor the bridges from our office itself. So as soon as there is some change or some misalignment or some damage occurring in the structure, we get an alert, and then when as and when we get the alert, only we go and check the condition. So it is like based on the condition based, not on the routine driven process. So because of that, we can increase the structure's longevity, and we can detect the damage in early stage to enable the, so as early as possible, we can prevent the damage or take the remedial measures. So in that way, the total cost also can be reduced. Moving on. So next, we'll see some terminologies used in structural health monitoring. One is system components. So system components, like, for example, you take an example of a computer. So for a computer, we have different components, such as a monitor, CPU, etc., hard drive, whatever it is. So different components are there. Similarly, for the structural monitoring also, we install the sensors. So here we can see the tall building. So at different location, we install the sensors. Here, this is a bridge. So this is a suspended bridge. So wherein we can see at various locations at the deck as well as at the poles, we are installing the sensors. So this is another image showing the sensors. So this example, so this bridge, if you are considering, we can see the various sensors there. And then these sensors are connected to the data acquisition system and the communication system. So the communication is, so it is connected through the internet, and then we can process the data automatically, or it can be manually as well. And then we'll store the data. And then from this, we can do from this data, we can do the analysis. Okay, so these are the system components in structural health monitoring. Now, let us see what all has to be monitored and how. For example, we can monitor the load, right? The load acting on a structure, or how much is the external load acting. So that can be monitored. The deformation, how much bending it has occurred, or to one direction it has tilted. So what is the deformation? What is the strain? Is there any temperature variation? We can also monitor the acceleration, the speed, wind speed, pressure, then also acoustic emission. Okay, and also nowadays we follow this video monitoring, and we can also monitor the corrosion rate, how much corrosion has occurred in the reinforcement, how much cracking, what is the extent of cracking, what is the strength, tension, location of distress. So all these parameters can be monitored, right? And we will see how. So how means first step for every like non-destructive testing method is a visual inspection. For example, now also if you visit, if there is a distress in any structure in your vicinity, the first step you have to do as a structural engineer or a health monitoring engineer is that you have to visit the site. Then only you know to what extent the damage has occurred. So this visual inspection includes, so nowadays it is not only like simply going and seeing, we can also use the small equipment. So for example, there is a column which is under distress. So this person is investigating. Okay, we can also send drones, right? We can also use the drones to take the images. So we can control from the nearby location, and then we can take pictures. Then from this, we can find out what is the cracks, where is the crack has occurred, and all we can find out. So this is known as the visual inspection. So we can do this laser scannings, drones, as well as digital photogrammetry for visual inspection. So this is the simplest approach. The simplest approach is visual inspection, but it requires full experience, because based on experience only we can draw the conclusion from the visual inspection. What has to be done? What data has to be taken? What is the inference from this data, etc. We can find out the irregularities in the structure, also the discontinuities, whether it is out of plumb, whether it is vertical or not. What are the cracks occurred, or is there any settlement? So all these things we can analyze using the visual inspection. We can also get a detailed geometric, material, and technological survey based on this visual inspection. So we can generally nowadays we are using this drone survey for this visual inspection. Now, continuing, so we discussed we can monitor the strain, temperature, acceleration, wind speed, pressure, acoustic emissions. So these are the equipments which can be used to measure these things. For example, the load cell is to measure the forces. So load cell even can be used in our laboratory to measure the forces acting on the structures, or for some experimental investigation, we can use this load cell. LVDTs are linear variable displacement transducers, differential transducers. So these are transducers which are kept in a structure or an element to understand how much displacement has occurred. So this is an LVDT. And accelerometers. Accelerometers are used to measure the acceleration. So to analyze the dynamic characteristics of the structure, we have to use this accelerometers. Also the strain gauges. Strain gauges are used to measure the variation in strain. So various other techniques which can be used are, other than using this camera, we can also use this laser test, wherein, so this is a structure wherein there is a crack or an anomaly. So using a laser source, we put a laser here, and then using a polarizer and a shearing device, and we can process that image and get the result. So we can process how the crack has occurred, or what is the pattern of the crack. So this laser test can be used. Otherwise, we can use a sonic test. So sonic test, wherein we have this transducer. Okay, there can be a receiver and a transmitter and a receiver, and then the crack is there, or crack or some anomaly or some void, anything can be there. So we are passing this ultrasonic pulse, and then in the receiver we can get the, or we can get the, we can get how much is the wave coming, and then based on that time taken to transmit this from this end to this end, that is from the receiver to the transmitter, we can get from that data, we can find out the quality of this structure or quality of this element. Similarly, another method is infrared thermography, wherein we will put some energy source and infrared waves. And when this infrared waves are hit on the surface, it will emit some thermal radiation. Based on that, we can find out how much is the, or what is the crack, what has happened to the structure. So in structural health monitoring, we have static-based structural health monitoring, wherein the damage will alter the static properties. So the static properties, in the sense, we can consider displacement, rotation, slope, etc. As well as we have this dynamic or vibration-based structural health monitoring, wherein the damage will alter the dynamic properties of the structure. So when I'm talking about dynamic property, we tell about the frequency or time period, so which gives the quality or how much stiffness of the structure has occurred. So all of you would be knowing what is frequency. So I'll be just introducing some terms in structural dynamics, so it would be more clear to you. So frequency, everybody would be knowing, but what is model analysis and all, in the subsequent slides, I will just explain in this context. So frequency is nothing but number of oscillations per second. So So this is one oscillation. So this is our amplitude. This is a wavelength. So this frequency, so this time period also can be measured from this. So from this, we can measure the stiffness, how much the structure is stiff. So that measurement can be understood from this frequency. Then from the dynamic analysis, we can get the mode shapes of the structure. So I will explain what is mode shape. Before that, from mode shapes, we will understand how the deformation has occurred, or how much is how the structure is vibrating when an external force is acting, or due to the natural frequency, how much deformation is happening for a structure. And also the damping effect. So from the damping, we can get the detect the internal changes which has occurred in the structure. So to go into more details about mode shapes, just to give you an introduction. So when a structure vibrates, it does not move randomly. It vibrates in a particular pattern, right? This pattern is known as the mode shape. So let us consider this structure. So it is a cantilever. So yeah, we can see this one. So this is fixed at the base, right? So it can move like this. So this is a general all together motion, whereas it can be split it into the first modal shape, like it is moving like this, and then the second modal shape, the third modal shape. So it can vibrate in different modes. And it can vibrate in torsional mode, it can behave differently. So all these we can generate in our finite element analysis. So each mode shape corresponds to a specific natural frequency. So this shape shows how the part of the structure move relative to another. For example, this is a mode shape. This is a first modal shape. So this point, how it is moving with respect to the original structure, that idea we can get. So some points may move a lot, another points may move only a little, and some may remain stationary. So the points which remain stationary are known as the nodal points. For example, here, these are the nodal points which does not move. So this is a base idea about the mode shapes. So these mode shapes are independent of the external forces. They depend only on the structure's mass and stiffness. So once we get the data, we can find out at which mode it is vibrating. So based on that, we can find out how much it has deformed. So this mode shape helps in identifying the critical regions prone to damage during the vibration. So different regions. So if you analyze the structure and get the mode shape, from the mode shape, we can understand what are the critical regions which are prone to damage. So all the regions may not be critical. So we can identify those critical locations and suggest the repair methods. Now talking about damping. So damping is a mechanism by which vibrational energy is dissipated in a structure. For example, suppose an earthquake is hitting on a structure, so it will absorb that energy. That vibrational energy is absorbed by the structure, and that has to be dissipated slowly. So that process of dissipating is known as damping. So here we can see initially it is very high, then you can see the vibration, it is reducing. So that is the effect of damping. So this due to this damping, yeah, we can see like a structure, for example, bridge or building. When it vibrates due to wind, traffic or earthquake. So due to this damping, it reduces the vibration over time, bring the structure back to rest. That means during this heavy wind or earthquake, the structure will absorb this energy, and if this energy is dissipated in a second, then severe damage will occur. But we have to channelize it in such a way that it is having some damping, or properly or slowly the energy is dissipated. Then the impact on structure would be less. So for that only we introduce dampers to the structure. So it prevents excessive vibration and also protects the structure from fatigue or failure. It also improves the comfort and safety, especially in tall buildings. In the tall buildings, the critical problem is due to the wind forces. So when the wind is hitting, we feel like it is getting shaken. So for that, we install dampers in the structure. So due to the effect of dampers, the energy will get dissipated and we won't feel that much effect. So that means we get more comfort. So having introduced these terms, we are discussing about the dynamic vibration-based structural health monitoring. So after collected the experimental data, so we'll go to the field, put some accelerometers or whatever it is, or ultrasonic pulse velocity, UPV, and then we collect the data, and the analysis of structural behavior and assessment of global health is generally accomplished by using a numerical model. And we take this data and make a numerical model or FEM model. And then we'll do this model analysis. So operational model analysis is where we take this, we identify the system. So we initially told about system identification, wherein we find out the frequency, mode shape, etc. And then we will collect those things and then put it in the numerical model. And in the numerical model, we run the analysis, and if in the and also we collect it from the site and we will update the model. So that is known as a baseline model. I will explain these terms once again for your clarity, because these are structural dynamics terms. So I don't know, everybody may not be familiar with those. So once again, I'll explain. So here, after getting this baseline model, we will so this model is used to determine the response of the structure under different conditions. Then we will create this FEM model, and then we will put some other data, like we want to know whether the structure withstands earthquake. So we'll put the earthquake data into it, and then we will predict how it is behaving, and then accordingly we predict we propose the remedial measures. So so what is a baseline model? So baseline model is numerically, so use numerical model of a structure. So usually finite elements model. And then it is built using the initial design data, such as a material property. So material property includes finding the Young's modulus, Poisson's ratio, etc. We find out the material property. Then we find out the geometry of the structure. So how we'll get the geometry of the structure? We can find it using the drone survey, and we put the boundary condition and then represent the theoretical, or so this baseline model represents the theoretical or expected behavior of structure before any damage or alteration. So it is a base model. So what we do is that measured model parameters, so measured frequency. So model parameters, properties imply frequency, a mode shape, etc. So that we will feed into the baseline model. Then we will compare with the actual real structure. Then we identify how much it is changing, how much is the discrepancy. Then we will update the model. So that is a process. Then we so here this numerical model updating. So it is generally two terms. So model in the sense numerical model and model. So it since we are putting the model property, for example, mode shapes. So there it is known as MODAL. Model updating. So both the terms can be used. So the process of adjusting or refining a numerical model so as to predict the dynamic behavior. So dynamic behavior in the sense natural frequency, mode shapes, damping. So matches the measured data from the actual structure. So we will take the readings from the actual structure also, and then we will compare, and then we will update the model. So these are the steps involved. So measure the model properties from the experiment, like we use the accelerometer to get the mode shapes, frequency, etc. Then compare with this model property predicted by the baseline finite element model. Then we will see what is the discrepancy, is there any change. Then we will update the model parameters. So this is the overall process involved in the structural health monitoring of a building. So let us see what type of structure was used, and we will discuss the case studies. So in this research, we use the slender masonry structures. So slender structures, you know, in the one dimension is very big. So it is a height here. A height is very larger compared to the other dimension. So that is known as a slender structure. So considering the historical importance, we have considered the masonry minarets. So minarets are integral part of architectural heritage. So they have suffered damages from natural disasters, and particularly they are very vulnerable to earthquakes. So in India, we have many masonry structures. So these masonry structures shows this Indo-Arabic design or Islamic combination of Hindu-Islamic traditions. So assessing their current condition and integrity is important. And there is a need for proper assessment to address the actual behavior of these minarets for their conservation and preservation. So, for example, these minarets are very vulnerable to earthquakes. So, here in this figure, so figure A, we can see the minarets before and after the earthquake, Turkey earthquake in February 6, 2023. So, here you can see this is a mosque part. You can see a dome shape. Are you able to see? Am I audible?
Yes, ma'am.
Okay, okay. So here you can see the dome shape, and then here there is a minaret in the first figure. Whereas here, this figure shows it after the earthquake. So here, can you see the minaret over here? So we can see only the dome structure. The minaret is all damaged. So it is no more here. So the minaret's here. The minaret you can see here is not here after the earthquake. So it has been completely damaged after this earthquake. Similarly, here, this structure, this slender structure is a minaret. So here, after the earthquake, we cannot see the structure. So these minarets are representing the Islamic culture. So especially to earlier days, they will call for prayer. So for that, they will go to the top of this minaret and call for the prayer. So nowadays, they are using this sound systems and all, loudspeakers and all we'll use. But earlier days, this was a system to wake people up early in the morning for this prayer. So it is a slender structure. It is a cantilever-like structure. So it is sensitive to horizontal dynamic loads such as earthquake, sometimes wind, or even traffic. So this is a classic structure, a classic minaret structure. So it is having a foundation. Then it is like, generally it is a circular in shape, and it is having a balcony, right, and an upper part and spiral cap, and at the top we'll see an ornamental portion. So this is a cross section at the balcony level. So here you can see we can get there will be normally spiral staircase to get into the top of the structure. So so these are some of the masonry minarets in India where we have went and collected data. So first one is a Chand Minar. It is located in Aurangabad, Maharashtra. This is Julta Minar in Ahmedabad, Hiran Minar in Uttar Pradesh. So different parts of India, we have went and taken this data. So these are nationally protected monuments. So in collaboration with Archaeological Survey of India, we could get the access to these minarets to take the readings. So, so totally there are 3,696 nationally protected monuments and 42 World Heritage Monuments or sites. So the workflow was like this. So first we went to each site and then field documentation using geometrical drone surveys and NDT. Excuse me. So first we went to the site and did this drone survey to get the geometrical details. Then we prepared a baseline model using finite element software. Then, as I discussed, the model updation was done and using some empirical relations and the system identification results. So, for example, finding out the frequency, modal shapes, etc. Then, so after this model is calibrated or updated, we did this dynamic analysis and also to examine the horizontal drifts and stresses in the minaret. So this was a workflow adopted. So first thing was this DJI Air 2S drone was used. So like this, the flight was set, right? And then, for example, here you can see the drone here. So from this drone, about 300 to 400 photos of this minaret was taken, right? And from this, we could get the geometry of the structure. So first building, let us consider the Chand Minar in Maharashtra. So it was built in 1445 AD. So this Chand Minar consists of an arch, plinth, and it's a tower made of the local basalt. And this exterior portion is covered with red sandstone. You can see how beautifully it is aligned. And the internal spaces, it is coated with white plaster. And it has 24 chambers and small mosque at the base, right? And then there is a catacomb-like structure where it's like a tomb. Like at the bottom also, we can see a catacomb-like a structure. So this is the details of the Chand Minar in Maharashtra. So, during the field documentation, so this is a ground floor. This is a plan at the mosque level. This is a plan at the minaret level. So this is a ground floor level. Okay, so at the ground floor, we can see the staircase going up. So when we reach the next level, we will see the mosque level. So from the ground floor, if you take this staircase, we'll reach this mosque level, this figure. So there it was used for the prayer and all. And then again, when we take this spiral staircase, we come into the minaret level, right? No, it's not a spiral staircase. Again, the staircase we take, we'll get it to the minaret level. From the minaret level, it is a spiral staircase to the up. So this is how it looked like. So next study was in Hiran Minar, Uttar Pradesh. So this Hiran means deer. So this structure was built using the Mughal time. So it was built by the Emperor Jahangir. So he has a favorite deer. So after the deer died, he kept this place as the monument for the deer. So this base region, so that is where his deer tomb or whatever. So that is the that is how the name, the Hiran Minar in Uttar Pradesh. So it is a square platform structure. Then there is an octagonal plinth. So you can see it here. It's a square structure, then octagonal plinth. And top of that, it is this minaret. So if you look closely, so this also shows how much animals were involved in the historic times. So for example, you can see like these, whatever it's projecting here, it is actually the elephant trunks. So it is said that when these emperors win a fight or win a war, so they take all this elephant trunks and then paste it over here to show a sense of victory. So they collect it and put it over here, but now it is not really the original ones. We can see it is actually thickly plastered cream white structure. So it is actually made of like plaster of Paris nowadays, but earlier it used to be the real elephant trunks. So yeah, so this is another minaret, that is Hiran minaret from Uttar Pradesh. So last number of elephant tusk, like vertically, like 15 in 15 rows were there. Okay, 15 rows having the elephant trunks was there. So this is the structure. Then the third study, we went to Jhulta Minar in Gujarat. So it is known as Jhulta. Jhulta means it is shaking, it is moving. So the speciality of the structure is that it is having two minarets, so set of minaret. So if there is a disturbance in one structure, the other one also will vibrate. So that is known as the Jhulta Minar. So it was actually destroyed in 1753 during the war between the Marathas and Mughals. And only two minarets are existing nowadays. So this is the one side, right? And Raja Bibi Mosque, which was dismantled in order to study the construction, but they could not keep it back. So people were curious why. So as I told you, if one minaret is vibrating or some disturbance is given to one minaret, the other minaret will also shake. So to study what is happening over there, so under British Raj, that one portion was taken. So you can see here, the top portion was dismantled and taken for study, but they could not keep it back for they could not put it back. So now, yeah, this is the one. So only one place it is there. So that is the shaking minars, which has undergone many earthquakes. It is still there. So when we went and took the data in the Jhulta Minar at Sidi Badir Mosque, so this monument has two vibrating cylindrical minarets. So you can see two cylindrical minarets. So you can see my research scholar standing here. So he was the one who was going to take the readings and all. So this minaret is separated by a distance of 7.5 meters. And now we can see some horizontal steel belts which are kept. After some renovation, they have kept some horizontal steel belt to hold this. Okay, so this is the geometry of the structure. So we can see this. This is one minaret. This is another one, and there is a bridge in between. So at the bridge level, you can see two minarets here. At the minaret level, so somewhere here, you can see it is like this. And at the bottom plinth level, it is a cross section like this. So this is the cross section, total cross section of the minaret. And in both the minarets, we can go in the stairs upstairs, and we can look from this port. So, so these three places were visited and the data were collected, and we'll discuss about what type of data was selected and what kind of analysis was done. So to find the material property and characteristics of minarets, so since it is historic structure, we cannot extract the material and use it for laboratory testing and all. So it was all very much restricted. And some region, even for taking the readings, one more minaret was we could not include in the study because it was we could not go there and take the reading. It was Qutb Minar. There also, because of this restriction, we could not take any field investigation due to the restrictions. So so here we can see 5 regions or locations were tested. So in each region, 20 readings were taken. So we to check the material property, we use the UPV. UPV stands for ultrasonic pulse velocity. So here we can see at 2 locations. So I just showed you how the sonic method works. So here we have one receiver, transmitter and one receiver is taking from this portion, the vertical portion, and also from this beam, also from this column. The readings were taken and the velocity and modulus of elasticity was measured. So this was the instrument which was used for this UPV testing. So next is ambient vibration testing instrumentation. So ambient vibration testing is nothing but a non-destructive testing method used to assess the property of the structure. So here, from this, we can find out the natural frequency, mode shapes, and damping ratio. The dynamic properties can be obtained using this ambient vibration testing. Whereas by using this UPV and all, we can find out the material property. So this was the equipment we have used. So it is an accelerometer. So it was from Bean Service. So this is the picture. So here we can see these are the accelerometers which we use for this investigation. So a different location we are fixing this accelerometer. So here you can see the spiral staircase. Both ends we are fixing this accelerometers. So these sensors are installed on different parts of the structures, and the vibrations were recorded for a particular period. Then we have processed the data. Then we have performed the operational model analysis. So wherein, so the structure is there. So from different places, location, we will take this data, right? And so there was no external force which was applied because we cannot, this was the natural excitation which was used. So this natural, what is the response due to this natural excitation, and the frequency response was noted, and then the model identification function was found out, and this peak regions was noted as a mode, and the mode shapes was plotted. So from this we could find out the mode shapes from the peaks, the vibration. So we filtered the data and find out the peak region, and from that we could find out the mode shapes. And these things we are feeding it into the finite element model. So after that we are doing the seismic analysis using the data seismic records we are having. So in the system we have used this Artemis software for this analysis. So the seismic analysis was carried out, and then what is the strain, what are the stresses, what are damages or deformation which has occurred was identified from this FEM analysis. So in the same manner, so using AI techniques, we can do the same thing. For example, data collection. So data collection, it was here I have used only for like 3 different structures. So we cannot there is only one chant minar or one hiran minar. So the data collection we have to do it there itself, right? So from there we can either use mobile phones, we can take the drone data, even the cameras can be used to collect the data, right? And then we will clean the data and then label the data. For example, this picture shows a spalling of the structure. If this picture shows a cracking of the structure, this is some blistering. So like that, we will label the data. So from this images, we can label, so this is spalling. So if such images come, it is spalling. Such images comes, it is cracked. These are the blisters. So by using the deep learning tools, we can test from this data set, we can do the testing data set, and then from that we can detect the damages, and we can classify the damages. For example, classification of the crack based on the width, right? And whether it is dormant crack, active crack, etc. can be done. we can identify how much spalling has occurred, what is the efflorescence, or any components are missing. For example, here, if anything is missing or not. So such thing can be analyzed using the deep learning techniques. So coming to the summary and conclusions. So structural health monitoring helps in early detection and analysis of structures. So preventing the catastrophic failure and reducing the maintenance cost. So advancements in technology. So recent advancements in sensor technology, data analytics and machine learning can significantly improve the effectiveness and efficiency of structural health monitoring systems. So these technologies enable continuous real-time monitoring and provide valuable insights into the structural integrity of the assets. And structural health monitoring research and technology development will pave the way for more resilient and intelligent infrastructure systems. So this work was in a collaboration with Coalition for Disaster Resilient Infrastructure, CDRI. So it was a funded project from CDRI. And also with help of the Archaeological Survey of India, we could implement this project. And of course, the support from NIT Puducherry. So these are the references. If you have any questions, the session is open. Any questions? Am I audible?
Yes, ma'am. You're audible.
Yes, ma'am.
Yeah. Did I finish it too fast? If any questions, you can please ask. Is there any advanced equipments used for SHM in India as of now? Yes, actually, for example, this one. So this study we have done using this structural health monitoring, that is the ambient vibration testing. So it is implemented. So for example, so we have used these accelerometers and then found out the present condition of this masonry minarets. So it is actually used in India, right? Yes. Anything else? Did you understand? Was it too much into structural dynamics? I don't know.
Ma'am, one more question is in chat box
Okay.
from Amita. Ma'am.
Advanced techniques, no? Then Professor Manavalan. Okay, thank you. Okay, application and job opportunities in this field. Yeah. So yes, this is actually very emerging field, and we can also call it as forensic engineering, the structural health monitoring. So like forensic surgeon, how he does this process of investigation. So like that, this structural health monitoring engineer. So it is actually very good profession, and I think in Bombay and all we get very high paid jobs for this. So it is always because no, as there will be anyways the structures There will be different anomalies in structure, and we keep on finding out different in the structure. So as there are more and more constructions, we will definitely have this structural health monitoring. So it is really a good area to explore. Yeah, next question is, can we find out exact cost of past damages using this method, like for very ancient structures? So the cost of damage can be only assessed. Like it may be due to different causes, but to what extent it has undergone the damage and what remedial measures has to be done. So that can be more focused from these investigations, because the cost majorly because all the ancient structures might have survived a series of earthquakes, and also due to the age they have undergone the damages. So it is I think the more important more focus should be on how we can or what is the extent of damage and how we can rectify that. So these methods will help in that direction.
So participants, any other questions?
If there are no more questions, thank you for your patient listening. I hope you could follow something, because I didn't have much response, so I was just going in my own pace. So I don't know.
Okay, ma'am. So
Okay, thank you.
okay. So good afternoon all. On behalf of Department of Civil Engineering at Jyothi Engineering College, I extend our sincere gratitude to Dr. Nidhi M for delivering an insightful and engaging session on structural health monitoring systems. Dr. Nidhi explained the various stages involved in monitoring process with remarkable clarity, making even complex concept easy to understand. Her inclusion of relevant case studies added great value to the session, enabling all participants to gain deeper and more practical understanding of the subject. We are truly grateful to you, ma'am, for accepting our invitation and for taking the time to share your expertise with us. Your presentation was not only informative but also inspiring. Once again, thank you, Dr. Nidhi, for your valuable contribution on for making today's session a meaningful learning experience for all of us. Thank you, ma'am.
Thank you so much. Thank you.
Okay. So I think the feedback link is sharing. Okay, ma'am. So participants can leave. I will share feedbacks link.